Okay. 16, that's good. Okay. We're going to talk today is a major section of this. I would say the food chemistry is a whole semester. It's a very important concept under the reaction called a Maillad reaction. We mentioned a couple of times. We're going to talk about detail, and there is lots of the organic chemistry information there, so we want to mention. We want to go very detailed of all the reaction, but we want to mention some of them when it is important. Okay, before we go detail, talk about this reaction. Everybody should be know. Maillad reaction. This is created by a French scientist. Find what happened is a milk powder stay at room temperature for a longer time, then turns yellow. And this is the first phenomenon discovered by, the name is French Louis Maillad in 1912. So he's a person who is find this phenomenon and observed this phenomenon. Then there is all kinds of the research and explanation following that. Now, this one we all call it now enzymatic browning. But before we go to talk about the non-enzymatic browning, you need to know what is called enzymatic browning. Then you know the difference. Okay, what is enzymatic browning? A very easy example in our life every day. If you have an apple, okay, let's say you have a red apple. You peel it. You peel it. You put at room temperature for like maybe just 3 hours. It becomes brown. And the same thing if it's an avocado. Turns brown. That is called enzymatic browning. Why? Because in the oxygen, in the air, there is an enzyme called polyphenol oxidase. All these fruits, they are high amounts of polyphenol. Once they touch the air, exposed to the oxygen, there is a polyphenol oxidase there. Then become melanin. This indicates a brownish color. This is called enzymatic browning. And Maillad reaction do not need this enzyme. They do not require this enzyme. Well, of course, they may need oxygen, but do not require this enzyme to happen, to turn brownish color. That's why we call it non-enzymatic browning. Okay? This is the whole story. When they write, give you some introduction. What is Maillad reaction? This is the phenomenon you can see. A milk powder turns brownish or yellowish at room temperature for a couple of months if you don't store it very well. Okay, of course it's damaged. You cannot eat it anymore. Now, we want to mention to say, if we want to using some definition to description of Maillad reaction, you will say it is an amino group, of course, coming from an amino acid. Usually it's from an amino acid in a protein, and sometimes it's from a food products, in a food products. Reacted with carbonyl of a sugar. Then, or some people say this is a hydrolyzed oxyglycosidic. Some people say. They reacted, going through a series of reaction involved with polymers generation and polymerization, you can say. Finally become a product called melanoidin. And this is turns brownish to black color. If you want to say very layman and simple language. Now, before we move on to talk about anything detail, we want to mention two things. I better say you're not very familiar. When we talk about carbonyl sugar, this sugar needs to be a reducing sugar. Okay, yes, we take it out. So, Maillad reaction happened is on reducing sugar. What means reducing sugar? Which means some sugar treated as a reducing agent can involve in some type of oxidized reducing reaction. So why we call some of the sugar has is reducing agent? Because they have free available aldehyde. They have this guy right here. So I gave you an example. Glucose is a reducing sugar. This is glucose. Okay, right here. CH2OH. So here, HOH. OH, H goes here, HOH. Okay, now glucose. This is, we call it a cyclic. Closed like a ring. If it's open a ring, what's going to happen? It becomes, goes here, it will become. Okay, this is aldehyde, free available aldehyde. Now, of course, these are the same, I just skip it. And we also call here semi-acetyl. I want to make sure it's correct. We call it semi-acetyl. Okay? That's why this is we can be used. Once the ring is open, that's a free available aldehyde. So glucose is a reducing sugar. Same as sucrose. Sucrose is 5 carbon instead of 6 carbon. And something like this. Okay? Oh, sorry. Fructose. Fructose is reducing sugar because there's a free available aldehyde. How about sucrose? Now, sucrose is very sweet, sucrose. Sucrose is not a reducing sugar. This is not a reducing sugar. Why? Because sucrose is a disaccharide. It is composed basically with glucose and fructose. And this is we call acyl bonds. So sucrose do not have a free available aldehyde. They will not directly have Maillard reaction. How they become reacted in the food products? They need to be first break down this and become glucose or become fructose. Then those two can involve in Maillard reaction. So you need to know this non-enzymatic browning happens for reducing sugar, has free available aldehyde. This is one of the prerequisite requirements for that. Anything more than that, if it's not a reducing sugar, they need to be hydrolyzed or split become a reducing sugar. Okay, so this is something we want to mention. Second, why this thing happens all the time? A milk powder at room temperature becomes yellow. Why this is so phenomenal, so obvious that results? Because the major components of the amino acid in the milk is lysine. Lysine has epsilon amino acid, we call it. Why? This is what it looks like. This is the lysine. We say this is the alpha carbon. Carbon number 1, 2, 3, 4. Attach the 4 carbon with an amino group. This is called the epsilon amino acid. Any product that has lysine containing epsilon amino acid is very highly activated, will be involved in the Maillard reaction. Another one is alpha amino acid. We'll mention later on. Okay, so these two things you need to know before we go all detail. Milk containing lysine. And the milk also has reducing sugar, which is glucose or lactose. Some don't have lactose because some people will be lactose tolerance or intolerance, have the issue there. That's why this guy is a very sensitive, very vulnerable product for Maillard reaction. Okay, this is something we need to know before we go over. And here, very layman language, we talk about that. Now, how do we know this complicated reaction, the procedure? How we figured out that? Before we talk about detail, we want to talk a little bit about the results of the Maillard reaction. Maillard reaction in the food processing, most of the time coming from cooked or heated foods. It is very good. You have a bread, you have that crust brownish attractive color because of Maillard reaction. In these products, in these barbecue products, well, we can say that, we like it because of the Maillard reaction, those brownish color. We also think it has type of the antioxidants. For example, tocophenicol is there because of the Maillard reaction. They let those products extracted out. But also people will tell you, don't eat too much of the barbecue stuff or those highly cooked, roasted stuff because the nutrients will be gone. Amino acid, sugar, sometimes essential amino acid in a product. If you cooked it, they're gonna go. Last, they may generate some of the toxication material, which means carcinogenic material, that is also could come from Maillard reaction. Okay, so these are the things you need to know. There is a good thing, they contribute for the characteristics, properties of food products, but they also gonna lose nutrients and also will generate carcinogenic toxication material. So there is the two sides of the one apple, okay, good or bad. Okay, then we mentioned earlier, it's a very complicated reaction. Then, how do we know all the details? Because of this guy, John Hodge. He's a food chemist working in USDA ARS, which is Agricultural Research Service in Illinois. Back in 1940, 1950, he did the research for cereal science. Then, because similar to milk. There is a sugar, there is amino acids, all kinds of things. He read the paper, do all kinds of research the whole lifetime, and published one very highly cited, very famous paper titled Chemistry of Browning Reaction in Model System in Journal of Agricultural Food Chemistry. This paper back in 1953 has been cited maybe more than 2,000 times right now to well explain the story and the procedure behind the Maillard reaction. The paper is right here. I printed out. Our textbook, which is edited. Our textbook, chapter 3, from page 128 to page 136, which is described based on this paper, but only very concisely and sometimes a little bit confusing. I will tell you why. Because they take part of that schedule, the sketch, but not described in very detail. That's why a little bit confusing. So what we're going to talk about today, and or other textbook, or most of the lectures for the chemistry person, they will be using Hodge sketch as a guideline to explain the procedure of Maillard reaction. And he died, unfortunately, for cancer in 1996, and about 82 years old. And very unfortunately, we didn't give him a big prize, like Nobel Prize or any of those big awards. But his contribution the whole life for the Maillard reaction is pretty amazing, and equal to other major breakthrough in the science area. I would say it's a breakthrough in the food science or food chemistry area. So people always respect those two guys. We call it Maillard-Hodge reaction. Sometimes people say. We just commonly call it Maillard reaction. Okay. This is what comes out. What Hodge did for this sketch, or with this schedule, to talk about detail of Maillard reaction. So I'm going to draw on there, then Tim, you can move that video, then we can explain to you what happened and why this textbook or some other textbook which is kind of confusing you. The reason is I can explain to you. Okay, first of all, there is an amino group. Of an amino acids. Okay? They will be reacted, which calls hydroxyglycosidic group of a sugar. Now, of course, we already said it's going to have to be a reducing sugar. They will create a material. This material called N-substitute glucosiamine. This is the first initiation stage. I will break down this right there. This is the initiation stage. This we studied very well. We know kind of very well. Then the N substitute, glucosiamine, going through the second reaction called Amaduri arrangement. Then generate one amino, one deoxyketose. Sometimes we also call it ketosiamine. But you need to know the Amadura arrangement, there is a lots of alternative arrangement for that. modular arrangement is happened in carbon number 1. If it's happened in carbon number 6, called Haynes arrangement. Our textbook mentioned briefly, and I'll explain to you what happened. This second stage, also belonging to initiation, we can know that very well. We also know this quite well. Okay, once this guy generates, the 1-amino-1-deoxyketose generate, then the story becomes a little bit complicated. Okay, go this way, right there. If the condition is a little bit acid, in the acid environment, they're going to happen called 1,2 ammonization. Ammonization. This will be generated called Schiff base, losing 3 water, and this Schiff base will be further become HMF. What is that? Hydroxymethylfurfural. This is in this way, which is in an acid environment. How about in an alkaline environment? They go right here. It's the second one. If it's a little bit alkaline environment, they will basically lose 2 molecules of the water, then become a reductase. You can understand it, this is a modified reduced sugar. This will be further become dehydroreductase. Okay, not stop from there. This dehydroreductase, if they meet an alpha amino acid, then they're going through this pathway right here. This is called Strecker degradation. Strecker degradation coming through generate carbon dioxide, but more important is aldehyde. Now, this guy always contributes for the aroma. And also, this is a modified aldehyde. So people always say, this is a Strecker aldehyde. Okay, now, in the food products, nothing happens from this. They could directly, going through this, coming out another product, which is, we call it fission products. What are the fission products? Pyrovyl aldehyde or diacetyl. Pyrovyl aldehyde, COO, this is H, this is CH3, this is pyrovyl aldehyde. What is diacetyl? Very similar to that. COO, CO, CH3, and the CH3. These we call dicarbonyl. Okay, once these products generate, they all gonna go. Could it be a mix of the products? Could it be aldose? Could it be so-called alkylamine, could be ketones, or others, then these will be polymerized. I would say just the polymers, or polymerization, become a polymers, and finally become melanoidin. This is brownish color. Okay, now this we know, and in this secondary stage or intermediate stage, we kind of familiar with those. We already know some of the research done. But there is something still confusing people. Is this one could be here? This we don't know. Is this one could become here? Now, how these products have aldose, alkylamine, and ketones? This is still unknown. And what's the detail right here? This is still not very clear. Okay, so Maillad reaction, there is a 1 million paper, maybe thousands, hundreds, thousands of papers in the world. People do different food products. We know better initial and intermediate stage. The final stage, we were not very clear. And then what happened is, what's the problem for that textbook? People don't understand it very well. Our textbook, which is described here very well. Not a problem. Every textbook can describe very well. Our textbook, talk detail, is this part. Is only this part. So what we describe in the textbook is 1,2 aminorization or anorization. 2,3, this is called 2,3 anorization. Mentioned very briefly. This fusion products we mentioned a little bit, this structure degradation mentioned somewhere else, but not really logistics connected to these. Okay, that's why it's kind of confusing you. Now, in your general organic chemistry or chemistry book, what you're describing is this way. So if you look at the general textbook, chemistry textbook, they will describe it here, then go to talk about structure degradation. But they talk about these two. So that's another